Alright, in Chapter 10, we're going to be looking at intermolecular forces and how they affect our physical properties. Now, when we talk about physical properties, we'll talk about first just some of the easy ones, the obvious ones, melting points and boiling points. Now, biggest reason these change is because molecules are attracted to one another with different strengths, or some are held together more tightly. Those intermolecular forces are what is directly affecting these physical properties. Now, when we talk about intermolecular forces, we are talking about very temporary attractions. So what I have here is an example of some HCl, and HCl is got an imbalance of electrons, so part of the molecule is slightly more negative than the other part. You'll sometimes see this little Dipole symbol, and this side is slightly more positive. Now, we are still talking about the electron cloud. It's just that part of it is slightly more negative than the other part, and that creates small attractions. The negative of one HCl is attracted to the slight positive of the other, and that attraction creates an intermolecular force. The stronger that is, the higher boiling points we have. Now, some molecules don't have anything like that. So if I were to think about just H to H, there's no reason to expect that there's any imbalance on the electrons. So therefore, neither side should actually be more negative than positive. But on molecules like that, the electrons do move around randomly, and they create temporary imbalances. So sometime in its existence, HH might have the electrons totally on one side and making it slightly more negative. That creates a temporary attraction to another molecule. Now, for this to really factor into a large scale, we need a lot more electrons. Something like hydrogen, probably not going to do this too much, simply because it's only got 2 electrons. But if we get up to chlorine or bromine, we have those 7 more electrons from each, or 6 more electrons from each atom, for a total of 14. Going to help contribute to our temporary dipoles more. Alright, but we do see that with regard to these attractions, these temporary dipoles from non-polar molecules, molecular weight is a bigger factor on figuring it out. So if I even go with something more complex that's non-polar, so CH4 is a nonpolar molecule, it is going to have a certain amount of attraction to other methane molecules. But if I were to replace all those H's with, say, just fluorine, a lot more electronegative, it is going to create polar bonds, but the entire molecule would still be non-polar. But CF4 attracted to another CF4 is going to be a much stronger attraction, and it is directly proportional to, it's got more electrons. Alright, very predictable behavior. If I look at that with CH4 and just go down the periodic table and change the C to what's right below it, silicon, and right below it, germanium, and right below it, 10, I get a very predictable straight line. It's almost perfect in the sense that even though lead hydride is not on here, we could probably say it's right about here, PbH4, and get a very good, accurate call of it. And even if we were to somehow make more than the 2 atoms that have ever existed of fluorobium, FlH4 would probably be right up there with a measured value. But very predictable, very nice straight line, very easy to see that it is directly related to just the molecular weight. Alright, there are molecules that have the exact same molecular weight, but they're put together differently. What we have here on this far right, it is pentane. Now, pentane's made out of 5 carbons, and I'm drawing what we call the condensed structure. I'm not drawing out the CH bonds, I'm actually condensing them on there. But it's a nice straight line, all in a row. It's going to have a large amount of surface area. Alright, but if I take that same molecule and rip the two ends off and put them on that middle location, that's going to greatly reduce the surface area because it's now much more compact. And that's what we see over here with this thing called neopentane. And if you look, the boiling points are ever so slightly decreased. But branching affects it because it lowers the surface area. Alright, stronger than the nonpolar bonds or the dispersion force attractions is dipole-dipole interaction. This is just when the molecule itself has a polarity. So even if we go back to that CH3 or CH4 diagram we did, if we change one of those to just fluorine, for instance, that's going to create some, that's going to disrupt the symmetry. It's going to be a polar molecule. That molecule as a whole would be attracted to another CH3F with a much stronger attraction than is dispersion. So when we have two polar molecules, we get these dipole-dipole forces. And these are drastically stronger, so we have a much increased boiling point. Now, going back to just the Lewis structures, when we introduced the idea of nonpolar and polar, we, flat out do see that for the same molecular weight, a polar molecule is going to have a much higher boiling point and melting point than a nonpolar molecule. All right. Among the dipole-dipole interactions, there are a special class of ones. So water, for instance, has these very polar OH bonds, creating a very negative part and a very positive part. Well, that creates a very strong attraction between other water molecules to the point where we actually say we call it a hydrogen bond. Now, it is a type of dipole-dipole interaction, but we're specifically looking for an OH bond, an NH bond, or an FH bond somewhere in the molecule. And if you look, these three guys, the O, N, and F, are the three most electronegative atoms on our periodic table, and that is a factor. It's making a very polar bond, and it actually drastically increases the boiling points and freezing points, or melting points. Alright, so much so that if I were to do the same type of trend as we did on the CH4s, the nonpolars, we would actually come up with something like this. So I got H2S, H2SE, and H2TE. Those are all group 16s, and what's missing is H2O, which, if we imagine the line's going to put that right there. These are boiling points, though. And if you look at that scale, that's saying that it would predict the boiling point of water is going to be somewhere around negative 70 degrees Celsius. Well, it's nowhere near that. It's drastically increased. And all three of these, drastic change. Just the fact that it has an OH bond, or an NH bond, or an FH bond, it drastically increases the dipole moment. So much so that we actually see something kind of interesting. So, molecular formula of C2H6O can be put together two different ways. I can say CH3, CH2OH, which is ethanol, component of gasoline nowadays, and then CH3O, CH3, which is dimethyl ether. Sometimes used in sterno cans for like heating up food, and carburetor cleaner, if you remember what that stuff is. Alright, boiling points are kind of drastic. This is in the 70s, as in 70 degrees Celsius, as in it is definitely a liquid at room temperature. Now, you might think, since I mentioned sterno, that the dimethyl ether is going to have a higher temperature. Well, the reason it's in there, it's what's throwing you off is the that gel that makes up sterno is actually there just to keep it from evaporating. Carburetor cleaner, which hardly anybody's familiar with, is definitely going to come out as a spray. It's a gas. It turns out that the boiling point of dimethyl ether, which is what this stuff is around negative 20 degrees Celsius. So drastic difference. So they're both polar molecules, but the fact that this has an OH drastically shoots up its boiling point and melting point for that matter too. Alright, next little physical force we're looking at is viscosity. Now, going with two things that come up with viscosity often. Honey While it's not super common that we come in contact with a day-to-day basis, pretty much everybody knows what honey is. Syrup could fit in here too for like going to IHOP. And then motor oil. Turns out motor oil is also something that we use for its viscosity. In motor oil, we want it to stay relatively thick because that keeps it around. Yeah, we want it thin enough that it gets in all those nooks and crannies. For honey, we just want it to actually taste good. Now, if I go to IHOP with regard to syrup, they sometimes will heat that up. And the big advantage of having your syrup heated up is it flows easier. Same with like car oil. Like when you go to change it, if you were to change your own oil, it's generally a good idea to warm it up some before you change it. And that has to do with the fact that it will drain out easier or quicker. But both these are viscous things. Now, it turns out every substance has a viscosity, and here's a few of them. Like we have water's viscosity, which you have an idea of what water does if it gets in contact with you. It turns out gasoline is less viscous, and that is just regular old gasoline. Ethylene glycol is antifreeze, and if you ever had any contact with ethylene glycol, you'd probably have realized that it feels thicker. But to go up to like motor oil or honey, these are drastically higher. And something that I saw from your book, I think it was in your book, glass. I know you might have heard people say that glass is flowing and that it over time would actually get thicker at the bottom of the plane of glass. Well, it does actually have a viscosity measurement. It's somewhere 10 to the 17th or so. So it's kind of safe to say it's not flowing. But over time, it kind of does. I think you have more of a chance of the entire house collapsing long before your glass settles or flows downward. Alright, next intermolecular force we're looking at is surface tension. Now, surface tension is the reason water beads up on your car if you freshly waxed it, or what we're seeing on these spider webs where it kind of beads up, it forms little bubbles. Now, the reason this happens, we think about what's going on with our intermolecular forces in a water molecule. A single water molecule is going to actually be attracted to numerous little water molecules in it. Now, if we're down in the substance, inside a liquid, inside a drop, a water molecule that's well inside is going to be sharing those attractions in a full three-dimensional space. It's going to spread that attraction to everybody it comes in contact with. Well, the water molecules at the surface don't have that benefit. They don't have anything up here to really attract to. So it makes all of these attractions ever so slightly stronger. And it's just strong enough that the surface of water actually has a lot more tension. And sometimes we see some weird things like paperclip, which is definitely something that's heavier than water. You can actually get it to float on water because if you set it down light enough or the right way, it won't break the surface tension. Same thing with bugs. Some of them actually can walk on water because they don't break the surface tension. All right, we see that when we go to the lab. If this is representing a graduated cylinder, when we put water in our graduated cylinder, we'll see it curve up. Now, turns out that's not always what happens. If we were to fill up that same glass with mercury, the curvature is going downwards. Now, couple things going on here. This is surface tension. The water molecules are grabbing hold of each other and the mercury molecules are grabbing hold of each other and making a very strong surface. But the reason it's going up on the glass on one side and down on the other is more to do with what the glass is made out of. Now, glass is technically a crystal of silicon dioxide molecules. Even to the point I could put another silicon here and there's oxygen. And I could just imagine what the crystal would look like. Now, it's not a repeatable crystal. It's kind of somewhat chaotic. Sometimes 6-membered rings, sometimes 8-membered rings. But it makes little helices. It makes little bands, and it makes nice little strongs, attractions. Well, the oxygens and the polarity of the silicon dioxide make this slightly polar in a molecule. Well, the polar water molecule is slightly more attracted to it, so it gets pulled up. But mercury, which is metallic bonds, not compatible at all with silicon dioxide, is going to be repelled away from it. Now, we can do something in the lab now to really actually see this a little bit easier. So if we were to take a graduated cylinder, doesn't matter what kind we use, and if we're able to just get inside the top with some car wax, like the stuff we put on our cars, and then fill the water up to that point, it would actually, when it's not hitting where the wax is, we would have that normal cuvette going down, or curvature going down. But as soon as we hit where we've waxed the sides, I'll just write wax here, it would suddenly curve up. And it's because that coating of wax is stopping the water from interacting with the silicon oxide underneath. And it's safe to say that wax is a nonpolar molecule, which is why the water is repelled by it. Alright, next thing we're looking at is actually some of those numerical values for the strength of the surface tension. Now this is related a lot to those intermolecular forces, but it's also due to the structure itself. So some molecules are going to be higher, even though they have what we might consider weaker intermolecular forces. Great example is octane, which is a totally nonpolar molecule. It almost has the exact same surface tension of ethanol, which actually has hydrogen bonds. Now it's a little bit silly to try to compare those two because the molecular weights are drastically higher. Octane has a much higher molecular weight. And that's something to reflect on too, because while the molecular weights do factor into, and the type of intermolecular forces related to polar and nonpolar bonds, it does have a lot of overlap. And what I mean by that, octane does have a drastically high boiling point and melting point, even though it's a nonpolar molecule, and some are even higher. Matter of fact, the black part of an asphalt road is typically just very large chains of things like octane, maybe as many as 20 to 30 carbons in them. But that huge molecular weight jacks up the boiling point and melting point, and now it's a solid at room temperature. Alright, phase transition is something we're going to look at now, because this is relating to those intermolecular forces. So going from solid to liquid, melting and freezing, common phrases we've heard of. We're actually going to talk about, we're going to be using fusion rather than melting though when we talk about going from solid to liquid. From liquid to gas, that's vaporization and condensing. And somewhat less used, solid right to gas, that's sublimation, and gas right to solid, deposition. Those are a little bit less used words, but they are talking about transitions. Now, a phase transition happens simply because the kinetic energy of a molecule is fast enough to overcome the attraction. So let's imagine that that little dashed line is separating something that goes from a liquid to a gas. Now all that means is if the speed of the molecule, or the energy, the kinetic energy of the molecule gets to a certain level, it's going to escape and turn into a gas phase. Now the reason hot liquids evaporate faster has a lot to do with the fact that as we heat things up, we move that kinetic energy higher. And the higher it gets, the more chance we're going to have molecules that go into the gas phase. But even at a low temperature, even if this was 25 degrees Celsius, water is going to evaporate because it does kind of have some molecules that are fast enough. And we can see this. If you filled up a glass of water and just left it out, it'd take a while, but it would eventually go dry. All that water would eventually evaporate. So we know this happens. Just that hot water does it quicker. Alright, speaking of those vapor pressures we get, vapor pressures do increase for everything with temperature. Now, the weird thing is on this little dashed line up on the top, that's happening right at 101.325 kilopascals. Now, the reason that number is important, that's atmospheric pressure. What that's saying is, that is the atmospheric pressure. So whenever these lines cross that, what we're getting is something we call the normal boiling point. Normal boiling point. Now, that normal simply comes from the fact that if you're at sea level, this is normally when that substance should boil. Alright, but if we actually somehow lower that pressure, So go to Denver, Colorado, or even use a vacuum. We can lower that pressure, and then everything boils at a lower temperature. All right, but we might want to predict what the shape of this curve is or where it is. So we might want to be able to somehow calculate what the vapor pressure or what the boiling point is at 80 kilopascals for any substance. Well, there's a guy ages ago, well, two guys ages ago, Clausius and Clapeyron, that came up with a relationship, and it is this equation right here. And we're going to actually practice that on a couple questions right now. So let's bring up this and a calculator, and let's see if we can figure this out. So we're looking at isooctane. That actually is the substance that we use when they rate gas for your gas pump. So when you see like 82 octane or 83 or 87 octane, it's saying that it's 87% likely to have isooctane in it. Now, doesn't necessarily mean that's what's in it. It's just that's the standard everything's compared to. Alright, this is that Clausius-Clapeyron equation. It is something that's provided to you on the test, so you wouldn't have to have it memorized. Something weird, we can actually use this to find what we call the heat of vaporization. We're going to talk about that later on this problem. We're going to calculate it, and then we're going to talk about what it actually means. Alright, so to solve for this, we just need to come up here and assign some pressures and some temperatures to this. So I'll say this is T1, therefore this is P1, and there's T2, and this is P2. And now I just come in and plug things in. Now, the pressures, I don't have to worry about the units as long as they are the exact same. In this case, they are, so I'm not going to change them. I'm just going to essentially do 100 divided by 10, and then take the natural log of that. And that would be everything on the left there. And then we have EH of vaporization. Now, previously we had an R that was based on the gas units, the liters and atmospheres. This R, it technically is the exact same R. It just has a different unit on it. It's 8.314 joules per mole Kelvin. So it's just where the liter atmospheres were somehow turned into joules. All right, and we do have to do a conversion. We want the temperatures to be in kelvins. So 98.8 plus 273.15 is 372.0, and 34 plus 273.15 is 307.2. Alright, now back up to what we got after we actually did the natural log of the excuse me, P2 over P2 over P1. We're going to take that value and multiply it by 8.314. And then divide by this thing in parentheses. Divide by 372 inverted minus 307.2 inverted, and then close those parentheses. This is going to be a relatively big number. It's always going to be turned into kilojoules. So, and see this negative means our delta H for this particular substance is 33.8 kilojoules per mole. So the units we're going to use. Alright, now, speaking of that value, that kilojoules per mole, that delta H, it's kind of like talking about the energy you have to put into something to get it to go away when it's at its vaporization point. So, concept-wise, if you think about you're heating up some water to make some tea or whatever, you're boiling water, I guess college students, you're boiling water to make noodles. All right. Anyway, we're going to bring that up to a boil, and it takes a long time for water to boil away. You can actually heat water to a boil, and then it can sit there and boil for quite a while. Well, that's that heat of vaporization. The amount of time it takes for water at 100 degrees Celsius to boil away is proportional to this heat of vaporization, kilojoules per mole. It's related to the energy you have to put into it. All right, now if you have that, actually gives you some pretty neat things you can calculate. So we got benzene has a normal boiling point of 80.1, and it has a heat of vaporization of 30.8. We're going to use those two pieces of information to figure out what the boiling point is in Denver, where the atmospheric pressure is substantially lower. All right, turns out we're using that exact same equation. P2 over P1 equals negative of the heat of vaporization over the R, and then 1 over T2 minus 1 over T1. All right, this is what I'm going to use as my T1. And it says that normal boiling point, that actually tells me that P1 is atmospheric pressure. And in kilopascals, that was the 101.325 kilopascals. And I did choose the kilopascals because this was in kilopascals. And that's what we're going to call P2. So we're going to be solving for T2 on this one. So writing it all out, I have natural log of 83.4 kilopascals over 101.325 kilopascals. My heat of vaporization is going to be listed in joules, so it's 30,800 joules per mole. This is that new R we just introduced, 8.314 joules per mole Kelvin. We're going to solve for this T, but this T is 80.1 plus 273.15 gives me 1 over 353.3. Alright, now we're going to solve for that T right there. So, starting with 83.4 divided by 101.325 gives us this. And I'm going to take the natural log of that value. Gives this. Alright, now I'm going to multiply by the 8.314. And I'll divide by the negative 30,800. And I get this very small number. To that, I'm going to add 1 over the 353. That should be 1 over T2. So to get T2, I just invert that answer. And I get that the normal boiling point, or the boiling point in Denver, is 346.9 Kelvin. And if I wanted that in Celsius, I just minus 273.15 and see that the temperature, boiling points, dropped about 7 degrees Celsius. Alright, practice that. Probably one of the more complex type of math problems we've had in Chem 1. Typical of Chem 2, something to look forward to if you're going to be taking that soon. Alright, last little thing we're introducing is a heating curve, and it's going to lead into a phase diagram. Now, I do get a kick out of this called a heating curve because it doesn't really have a curve. It's got a bunch of straight lines. Now, maybe as an average, it's kind of got a curve aspect to it, but it's really a bunch of straight lines. Now, the reddish lines, we've actually calculated these before. If we think back to when we did our calorimeters, we had an equation where we calculated our Q based on specific heat and mass and the delta T, the change in temperature. Well, all we're really adding to it is the Q that you get when you boil things, when it goes from the pure liquid at the boiling point to a pure gas at the boiling point, so that vapor pressure. So to actually calculate this Q, you're going to use that delta H of vaporization that we just introduced on that previous page, But this time you'll be multiplying this by the amount in moles rather than the mass. And it turns out for the fusion, you have a similar equation that uses the delta H of fusion, also with the moles. Alright, but what this is going to translate to is we get this type of problem now, where we're going to take something, a substance, and we're going to heat it up. Now in this case, or cool it down, this case we're going from negative 15 up to 120, so we're heating. Problem with this going from negative 15 to 120 is water is going to start as ice here and turn into steam by the time it gets here. So it's going to go through some phase changes. So we got quite a bit we have to calculate on this one. What I mean by that, if I were to graph out what we think is going to happen, we're starting down at a low temperature at negative 15. Once it gets up to 0 degrees Celsius, the ice will start to melt. Once it's all melted, it'll start going up, and it'll keep heating up till it gets to 100, and then it's going to boil. And then after it all uses up all the heat of vaporization, then it'll go up the extra 20 degrees, 120. So we're going to be calculating 1, 2, 3, 4, 5 different Qs. Now, since I have it starting at a low temperature going high, I'm going to actually do that. So the Q down here, when we have just ice, is going to have the specific heat of ice. The units tell us how to do this. It wants grams, so I'm going to put in 135 grams. And the temperature change the ice goes through, it starts at negative 15 and it goes to 0. So 0 minus negative 15. Alright, not going to do that math yet. We're going to do it all at the end. We're going to do now Q for when it melts. We're going to call it fusion, because that's what we call melting in the science world, or at least chemistry world. So when ice melts, it uses 6.01 kilojoules of energy per mole. Alright, the mole is tricky here because I do use that 135 grams because that's the amount of ice we used, but I need to turn those grams into moles. 1 mole water happens to weigh 18.016 grams. That's going to turn that into moles. Grams will cancel, moles will cancel. We're going to get kilojoules for that value. Alright, now got Q for water. So it's 4.184 joules per gram Kelvin. Going to use just the mass of water because we want the masses to cancel. And the water starts at 0, goes to 100. Then we have Q for when it vaporizes. This kind of looks similar to the Q for fusion. Got 40.67 kilojoules per mole. And since it's moles, we're going to take that 135 grams and convert that into moles. And the last thing is for steam, or when water is a vapor. And I have a specific heat of 1.84 joules per gram Kelvin. The 135 grams, and the water goes up to 120 from 100 degrees. Alright. Let's see if we can calculate this. And I'll just start at the top since I can. So 1.84 times 135 times 20 gives me, I'm going to put these answers in kilojoules. So this is 4.97 kilojoules. Oop. Now 40.67 times 135 divided by 18.016 gives us Now this is already kilojoules because it was kilojoules there, so 304.8 kilojoules. So it took a lot of energy to boil it compared to going up that last 20 degrees. Times 135 times 100. This is the energy just to go from 0 degree water to 100 degree water. 56.5 kilojoules. To melt our ice, 6.01 times 135 divided by 18.016 is 45 kilojoules. 45.0. And the last one, to get ice from -15 up to the freezing point of ice, 2.09 times 135 times 15. That's 4.2 kilojoules. All right. Looking at the size, the vaporization is the most energy. To turn ice into ice, or to warm ice from 0 to water at 0 took 45 kilojoules, but that was slightly less than get the water all the way up from 0 to 50, or 0 to 100. But to get my answer, I'm just going to add all these numbers up. So 4.97 plus 304.8 plus 56.5 plus 45.0 plus 4.23. So grand total is 415.5 kilojoules. Assume I did my math all right. All right, but we're gonna need to know how to do something like this. I doubt you'd get this much math on a test question because that takes a long time to solve. But you will be seeing something like this with at least 2 different Q's that you'll end up using, probably 3. All right. That gets us down to our last couple things. The next thing we're looking at is a phase diagram. Now, most phase diagrams kind of look like this. Water has a slight different one. This melting freezing line goes up at this angle rather than like it's on this page. But what we're seeing here is what happens to our freezing points, boiling points, melting points, all those when we actually vary the temperature and the pressure. So if this was representing a substance like water, where the pressure is fixed to atmospheric pressure, we see as we warm things up, it goes from solid right to liquid, right onto gas. But I believe this one is actually CO2. And on CO2, the difference is the atmospheric pressure is down here. And CO2, if it was at a cold temperature, it goes from solid CO2 right to gas. That's where we get the dry ice idea. All right, but what we have here is this little curve down here is representing the sublimation deposition line. We have our melting point, freezing point line, and we have the boiling point line. Now, the melting point, freezing line kind of goes up to infinity. This goes just to this thing we call the triple point. But the triple point is where all 3 phases can exist simultaneously. You can have, if you get it at the right set of conditions, you can have water boiling, vaporizing, and freezing all simultaneously. And then the other little point here, it's called a critical point. This is kind of weird. If we go above this temperature or above this pressure, this area in this here, the substance is not necessarily behaving quite like a liquid or a gas. We call it a supercritical fluid. Now it has some interesting properties. We use it now to actually remove caffeine from coffee. And we can do this from green coffee beans, so unroasted. So what we do is we put our beans in here in this extraction vessel. Well, that's interesting. I must have bumped stop. That's okay. It's right here. But we put our beans over here in this extraction vessel. And what we're going to do is raise the temperature of this extraction vessel, and I believe it's right around 300 degrees Celsius and like 200 atmospheres. I forget the industrial conditions exactly. But it's a high temperature, high pressure. At that temperature and pressure, the CO2 behaves like a liquid and a gas simultaneously. And the CO2 is able to penetrate into those green coffee beans. Now once they're in there, they're able to actually dissolve out the caffeine. Now there's a few other things come out with it, but for the most part, the only thing that really comes out is caffeine. So coming out of this chamber, we still have that supercritical CO2, but the caffeine's dissolved in it. Once we let it come over to this vessel, all we do here is either raise the or lower the temperature or lower the pressure, get back below that, and actually let the CO2 go back to being just a regular old gas, and the caffeine just comes right out. We'll wash the caffeine out and then reuse that CO2 over and over. It's a great means to do this on industrial scale. Does a great job of removing a huge amount of the caffeine. Would love to do it in a chemistry lab, but the extraction vessels are not something you just build out of glassware or pieces of plastic. Alright, that finishes up this chapter, and we are good to go with preparing for the next.